Hey everyone. Some of you expressed some interest in a short little review video on some useful trig identities that we may be using for physics. This is by no means an all-inclusive list, as you know, I don't write the exams. I don't know exactly what's going to be on them or what we'll need to know. But I do consider myself to have a fair understanding of most of the useful trig identities, and so I thought I'd share them with you here. So after watching this video, you should have a pretty good knowledge of the trig identities that you should know. So it's important to remember that all trig functions, right, whether you have tangent, cotangent, cosecant, secant, they can all be written in terms of sine and cosine. So those are the first trig identities that are important to know. So obviously we have sine, right? So sine of theta. Okay, that's one of our basic trig functions. And then we also have cosine of theta. So these are really our two fundamental trig functions. And we can write all the others in terms of these. Okay, so it's important to know when we look at sine and cosine, right? Obviously, we know that if we have a triangle here, and this has to be a right triangle, right? Because we're doing right triangle trigonometry. And our hypotenuse, we'll say it's 1. If the hypotenuse is 1, right? Then the side length here, this is just going to be cosine of theta. And the side length here, this is going to be sine of theta, right? If I were to change this, such that this hypotenuse was h, then our side length here would be h cosine of theta, right? And h sine of theta, right? Okay, so that makes sense. So let's move this back to a 1, and we'll show you how you can logically reason out what tangent is. So 1, let's make this cosine of theta. Remember, cosine always gives us the horizontal component, the x component, if we're in Cartesian coordinates. And this is sine of theta. All right, and now we can ask, well, we know the tangent of theta is equal to the change in y over the change in x. Well, what is that equal to? Well, we know that the change in y, this side length here, is sine theta, and the change in x, this side length here, is cosine theta. So it's equal to sine theta over cosine theta. So that's a very important identity. Tangent theta is equal to sine theta over cosine theta, right? Okay. Now, what else do we need to know? Well, cotangent of theta is equal to, you basically flip these around. So cotangent of theta is equal to cosine of theta over sine of theta. So if tangent is sine over cosine, then cotangent is cosine over sine. So once again, if you ever forget what tangent is, just remember tangent of theta is the slope of this line, right? So it's change in y over change in x, or rise over run, right? Rise over run. And we know that the rise is sine of theta, and the run is cosine of theta. So therefore, tangent of theta is equal to sine theta over cosine theta. Cotangent of theta, it's just cosine over sine. So just kind of invert the fraction. The other ones, so secant of theta, I always just remember this as secant. That sounds like sine, but it's unintuitive. It's going to be 1 over cosine of theta. So for secant and cosecant, it's the one that it doesn't sound like. So secant sounds like sine because it starts with an S. So it's going to be 1 over the other one, cosine. Same with cosecant, right? Cosecant of theta is going to be equal to, well, cosecant kind of sounds like cosine because it starts with a C, right? But it's cosecant, so it's going to be 1 over sine. So these two are a bit tricky, right, to remember. But I always remember secant. Oh, okay, well, it's going to be the one that's not sine, so it's going to be 1 over cosine. Cosecant, okay. Well, here, it's going to be the one that doesn't sound like cosine, so it's going to be 1 over sine. Those two you just kind of have to remember. So in summary, you can work out what tangent is based on the definition of that it's the slope. Cotangent is just the inverse of that, and then secant and cosecant you just kind of got to memorize. I'm sure there's a way to work those out too. I just find it easier to just memorize those. So in summary, what do we have so far? In summary, we know that tangent of theta is equal to sine of theta over cosine of theta. We know that cotangent of theta is equal to cosine of theta over sine of theta, right? Just flip the fraction around. We know that secant of theta, well, the thing that sounds least like secant is cosine, right? So it's equal to 1 over cosine of theta. And we know that cosecant sounds like cosine, and the one that sounds least like it is sine. So it's 1 over sine of theta. That's how I remember it. These four are the holy grail, right? You need to know these. You need to know at least what are the trig functions in terms of sine and cosine. So those are very important to know. Now let's go on to some Pythagorean identities. So those are also very important. So once again, make sure you remember how to write each trig function in terms of sine and cosine. That's very important. Now, you probably already know that. So let's move on to the Pythagorean identities. And for this one, I kind of have an interesting way that I like to derive it. Let's actually use a brush here. Okay. So almost everyone knows that sine squared theta plus cosine squared theta is equal to 1, right? Now, why is this true? Well, this is true because of the Pythagorean theorem. We know that this side length, if we call this side length A, and we call this side length B, and this side length C, then the Pythagorean theorem says that A squared plus B squared is equal to C squared, right? And so therefore, if we plug in A is equal to cosine theta, and B is equal to sine theta, we get cosine squared theta plus sine squared theta equals 1 squared is just 1. So this identity is very easy to prove. Cosine squared plus sine squared is equal to 1. And that holds true for any right triangle. So now the question is, well, that's a very easy Pythagorean identity to remember. And most people do remember this one. But there's other Pythagorean identities, right? There's other Pythagorean identities. And those are sometimes harder to remember. Now, the good news is that we can derive all the other ones simply by looking at this one. So to derive the other two Pythagorean identities from this base one here that almost everyone remembers, all you got to do is to derive the first one, first divide both sides by sine squared of theta. That's all you got to do to derive the other Pythagorean identity. So let's work this out, simplify it. So that's sine squared theta over sine squared theta plus cosine squared theta over sine squared theta is equal to 1 over sine squared theta, right? Okay, sine squared theta over sine squared theta, that's just equal to 1, right? Plus, this is equal to cosine theta over sine theta squared, right? And then this is equal to 1 over sine theta squared. Okay, so what is cosine over sine? Well, that's cotangent, right? And we remember that tangent is equal to the slope, the rise over the run, and the rise is sine, and the run is cosine. So tangent would be equal to sine over cosine. Therefore, cotangent is equal to cosine over sine. So we have a cosine over sine squared. So we get 1 plus cotangent squared theta is equal to, now what's 1 over sine theta? Well, remember, we want to take the one of sine and cosine that sounds least like sine, so that's cosine. Sorry, that is going to be cosecant, right? Because it's 1 over this, so this is cosecant squared theta. So there's your second Pythagorean identity derived from this one that everyone remembers, just by dividing both sides by sine squared of theta. Okay? So there's another Pythagorean identity that you can derive on a test, an exam, a homework, and you didn't even have to memorize it, as long as you knew this one and you knew how to divide both sides by sine squared theta. Now, how do you think we derive the third Pythagorean identity? Well, it's very similar, except we divide both sides by cosine squared of theta. Who would have guessed? So, if we want to take this And we want to derive the other one. We're going to divide by cosine squared of theta. Okay, let's do it. So that's sine squared of theta over cosine squared of theta. Remember, sine is rise, cosine is run, so we automatically know that this is going to be tangent squared of theta, plus cosine squared theta over cosine squared theta. That's going to equal 1, right? Is equal to 1 over cosine squared theta. So tangent squared theta plus 1 is equal to 1 over cosine of theta is secant of theta. So we can rewrite this as this squared, secant of theta squared, right? So it's going to be secant squared of theta. Okay, there's our other Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. So notice, from this base identity here, we can derive the other two just by dividing both sides by sine or cosine. So that's a very handy fact that I use for myself whenever I want to derive the Pythagorean identities. Now let's go ahead and look at some other useful trig identities that are a little bit more advanced, but still probably pertain to this class. So arguably one of the most useful identities is knowing that sine of 2 theta is equal to 2 times sine theta cosine theta. This is called the double angle identity, right? Because you notice that we've doubled the angle in there, and so hence the name double angle identity. This is the double angle identity for sine, and that's kind of an easy one to remember. Now cosine has a few double angle identities. So cosine of 2 theta is going to be equal to cosine squared of theta minus sine squared of theta. That's one of them. It's also equal to 2 cosine squared of theta minus 1. And it's also equal to 1 minus 2 sine squared of theta. So these identities here, the double angle identities for cosine, I just recommend memorizing. I don't really have any tricks here to memorize these. These I just recommend memorizing. This one has just been ingrained in my brain for so long that at this point it's kind of second nature that sine of 2 theta is 2 sine theta cosine theta. The double angle identities for cosine I just memorized, to be honest. So we've gone over how to define all the trig functions in terms of sine and cosine. We've gone over how to use the base Pythagorean identity, which is derived from the Pythagorean theorem, to then derive all the other Pythagorean identities. We've gone over the double angle formula for sine, the double angle formula for cosine. And now I'm going to get onto some more advanced stuff that we might not need for this class, but I thought I'd throw in here just in case we might need it, because it has helped me in classes such as calculus before. Okay, so the two extra things I wanted to add in here that you probably don't need to watch for this class, although you may, so I thought I would just add them in here, is we may want to know how to take the derivative of inverse trigonometric functions, and we may also want to know how to integrate trigonometric functions that are squared. So let's go ahead and start with taking the derivative of things like sine inverse, cosine inverse, so on and so forth. So here, the way I like to memorize this is I like to make a chart. I like to write S, T, S. And here, we start with sine theta, sine inverse of theta. Remember, we're taking the derivatives of these. Tangent of theta, secant of theta, STS, and always start with sine. And I always just remember starting with sine because it's one of the two most fundamental ones. And so if I have STS, I'm going to start with sine. T is obviously tangent, that's the only one it could stand for, and then the only other S left is secant. And these are all inverse functions. And the way I remember them is I remember the ones that have an S in them have a subtraction sign. So it's going to be 1 over the square root of 1 minus theta squared. This one has a T that looks like a plus sign, It's going to be 1 over, there's no root, 1 plus theta squared. And then this one has an s in it. That's like a subtraction sign. 1 over the square root of theta squared minus 1. Notice the difference, how sine is 1 minus theta squared under the root, and secant is theta squared minus 1 under the root. So that's just a subtle difference. But you know that tangent is the oddball out, because these have the s's, that it helps me remember subtraction with the root, and tangent has just the plus. The t kind of looks like a plus, so it helps me remember it's just 1 plus theta squared. So these are how I memorize these. Now, if you want to do the other ones, what I do is I say, what matches with sine? Well, naturally what matches with sine is cosine. Naturally what matches with tangent is cotangent, so just take all the cofunctions. Cotangent. And naturally what matches with secant is cosecant. And the derivatives of these inverse functions are literally just the negative of what they match with. So here it would be negative 1 over 1 minus theta squared. Here it would be negative 1 over 1 plus theta squared. And here it would be, an equal sign, here it would be negative 1 over square root of theta squared minus 1. So literally, these negative signs are the only thing that I've added to this side of the chart. So whenever I'm trying to remember what the derivative of a trigonometric inverse function is, I always just use a chart like this, where I first always remember s, t, s. These s's stand for subtraction. This one must be tangent. Start with one of the most basic trig functions, that's sine. The only s that is left is secant. And then I fill these in, right? I know that this has a subtraction. You kind of just got to remember this is 1 minus. And this over here is theta squared minus 1. And then tangent, that's just 1 over 1 plus theta squared. And then these, sine goes to cosine, tangent goes to cotangent, and secant goes to cosecant, and you just literally add the negative sign. All right, so that's how I memorize the derivatives of inverse trig functions. This was particularly useful in calculus class to memorize those. And the final thing I wanted to go over is in case we ever have to integrate, so in case we ever have to integrate something like cosine squared theta d theta, right? This can be quite a daunting task, unless you know some cool, at least I call them power reducing formulas for sine and cosine. And this is getting, I think, a bit advanced, but who knows? We may run into this in our course. I'm really not sure. So I thought I'd go over it anyway, because it's something that I've committed to memory and something that I've found useful in a lot of math classes. Okay, so here are the power reducing identities. Sine squared of theta is equal to 1 minus cosine of 2 theta over 2. And cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. Okay. Now, tangent squared of theta is equal to, it's literally just this over this. So it's 1 minus cosine 2 theta over 1 plus cosine 2 theta. So it's just that. So these are these are power reducing formulas, because you notice that they take a sine squared and they spit out something without a trigonometric function squared. So let's go ahead and see how useful these can be by solving this integral up here using these identities. So we'll take this cosine squared. That's what we're going to use. So this integral is equal to the indefinite integral of 1 plus cosine of 2 theta over 2 d theta, right? We know that is equal to the integral of 1/2 plus cosine of 2 theta over 2 d theta, right? we know that is equal to, in fact, we can, so we know that is equal to the integral of 1/2 d theta plus the integral of cosine of 2 theta over 2 d theta. Well, what's the integral of 1/2 d theta? That's simply equal to 1/2 theta. And then we're going to do plus this integral here, this integral of cosine 2 theta over 2 d theta. All right, so let's get some more room here for our work. All right, so we've solved our first integral here. We took this integral, well, we took integral of cosine squared theta, and we were like, how the hell are we going to do that? But then, once we realized that our power reducing formula allowed cosine squared theta to be equal to this thing, which is much nicer for integration, we could then split it up into two integrals, integral of 1/2 d theta, and integral of this guy, d theta. The first one's trivial to solve, 1/2 theta, and then we're just solving this one here. So when we solve that one there, let's just rewrite it here. So to solve this integral, we're going to need to do a u substitution. So here I'm going to let u is equal to 2 theta. Therefore, du d theta is equal to 2. And now what I want to do is I want to solve for d theta, right? Because we're essentially going to plug in, we're going to solve for d theta in this equation here, and then we're going to plug that result in right here for this d theta. So I'm going to solve for d theta. So the first thing I'm going to do is I'm going to invert both sides. So that gets d theta over du is equal to 1/2, right? Which is the inverse of 2. And then I'm going to multiply both sides by du. So I get d theta is equal to 1/2 du. Okay, cool. So now we have d theta is equal to 1/2 du. So I'm going to substitute in I'm going to substitute in 1/2 du for d theta. So this becomes the integral of cosine of u over 2 times 1/2 du. All right. Now that is the same as the integral of cosine of u over 4 du, which is the same as 1/4 times the integral of cosine of u du. Well, what's the integral of cosine? Well, let's think about this. The derivative of sine is cosine, and the derivative of cosine is negative sine. So the integral of cosine should be positive sine. So we're going to get 1/4 sine of u plus c. And let's go ahead and sub in. We know that u is equal to 2 theta. So it's going to be 1/4 sine of 2 theta plus c. So now this is our answer to the second integral. So we'll go ahead and plug that in up here. So this is equal to the answer of our first integral plus 1/4 sine of 2 theta plus c. So that's just an example of how you can use the angle reducing formula to take an initially daunting task and turn it into a fraction that seems reasonable to integrate via some basic integration rules and use substitution. So yeah, just thought I'd make this video to review this type of stuff. As a review, we went over how to write all the trigonometric functions in terms of sine and cosine. We went over the double angle identities, which can prove to be very useful. We went over the Pythagorean identities and how to derive those. We went over sort of a technique for memorizing the derivatives of inverse trig functions. And now we also went over using the power reducing formula for sine and cosine in order to better evaluate integrals that have sine squared and cosine squared in them. So that's a pretty good review of at least what I remember from high school trigonometry and calculus and physics. And these are the things that, at least in my opinion, you're going to see most often. There's probably going to be other things. Obviously, you want to know the derivative of sine is cosine, and the derivative of cosine is negative sine. But if you know that, then honestly you can derive everything else, right? So let's say somebody asked you, well, what is d theta of tangent theta, and you didn't know what that is. Well, you could say, well, that's just d theta of sine theta over cosine theta, and then you could use the quotient rule. And so basically, if you write it like this, and you know your calculus, and you know the quotient rule, well, you know the derivative of sine, you know the derivative of cosine, right? Low d high minus high d low, square the bottom, away we go, however you were taught it, right? You know the quotient rule. You can figure out that this is actually equal to 1 over cosine squared of theta, which is the same as secant squared theta. So I wouldn't stress about memorizing what's the derivative of tangent, what's the derivative of cosecant, right? As long as you know the derivatives of sine and the derivatives of cosine, you can always derive this on the fly. Same thing with the Pythagorean identity, no sine squared plus cosine squared equals 1. You can derive the other ones on the fly. The only things that really require the brute force memorization are probably the double angle identities and the power reducing identities, and also the derivatives of inverse trig functions. Although, as I showed earlier, there are tricks to help you memorize the derivatives of inverse trig functions. So this is just a little trigonometry review and calculus with trigonometry review for anybody that finds it helpful or anybody that's struggling to remember these trig identities. Remember, everything can always be written in terms of sine and cosine as long as you're using fractions and squares and things of that nature. So if a problem's getting too hard, just write it in terms of sines and cosines and see if you can get anything to cancel out. And remember your sine and cosine identities. Other than that, that's about it. Hope this helped. And if you have any other questions about trig in this class, or in another class for that matter, be sure to let me know.